Okay, I think we can start. Christian, can you share your screen?
I will. Okay. So today I will give you a little bit of an historical perspective. Can you still see the slides?
Yes.
Even as I turn them?
Yes.
I will give you a little bit of an historical perspective on the liquid argon dark matter program at Grassasso, starting from its origin with the warp program. And let me restart with a slide that gives you the sort of rationale that it's important to establish the case for a noble liquid detector for dark matter. These targets are excellent scintillation media, very abundant scintillation light, well beyond what is available and what is possible with crystals. And they are also excellent ionization detector. As we said the other time, there is no self-attachment of electrons to the atoms because they have complete shells. The photons are not self-absorbed. The materials are easily purified, and there is an excellent background discrimination. Time projection chambers. This is a slide from a period in which people were trying to develop detectors with fused silica domes. There was an intense development of the so-called cupids, utilizing fused silica domes to have ultra-pure detectors for light. And this was fairly recently, was something like 10 years ago, and the field of this development was completely abandoned because the field was taken by the storm by the silicon photomultipliers. So you have, anyhow, in the scheme, a drift field, which is stronger, much stronger in the region of the ullage at the top of the chamber. And when you have a WIMP scatter, you get the first scintillation light, which is spread essentially uniformly across the entire detector. And then you have the ionized electrons that move up in the ullage and give a signal which is clustered on the top layer of detectors. So what is the big difference between the xenon and the argon detector? The discrimination in xenon is based essentially on three things. Fiducialization. The background gets strongly reduced in the center of the detector with respect to the periphery just by the abatement of the radioactivity that comes from the self-shielding power of the xenon. The other important tool is the difference in the ratio of the prompt scintillation to the drift time delayed ionization. So that's something that we said also the other day. The ratio of ionization to scintillation, it's an important tool for discrimination in the xenon. It gives you a discrimination which is relatively contained at the level of 10 to the 2, 10 to the 3. And finally, the precise determination of the event's location in 3 dimensions. As we said before, due to the clustered concentration of events at the top of the detector, you can determine the position in X and Y in the range of 1 to 5 millimeters, depending on the size of the photodetectors. And the dimension in Z, the depth in Z can be determined to the level of 1 millimeter, thanks to the difference in time between scintillation and ionization. In argon, it's very different. In argon, it's very different because in argon, there is another very important tool, a fundamental tool. which is the pole-shape discrimination of the primary scintillation light. This is based on the fact that there are two components for the scintillation. There is the singlet and triplet emission from the dimers in argon. This difference between singlet and triplet is also present in the xenon-based detectors, by the way. But in the xenon-based detectors, the singlet and triplet, they decay with exactly the same time, a few nanoseconds, and therefore you cannot separate these two components of scintillation. In the case of argon, it's a fact of nature that the singlet and triplet are very substantially different in terms of the time of emission, 7 nanoseconds and 1.6 microseconds. In addition, there is a very strong imbalance in the population of these two channels, depending on the ionization density. For the minimum ionizing events, the ratio of triplet to singlet is 3:1. For the nuclear recoils, the ratio of triplet to singlet is 1:3. Okay, so there is a very, very strong imbalance. And if you just play with the statistics of these events, you will see that the theoretical identification power is huge. You know, if you detect only 60 photoelectrons, you can get a theoretical identification power, which is in excess of 1 part in 10 to the 8. In addition, you retain the difference in the ratio of the prompt scintillation to the drift time delayed ionization, the difference in the ratio of FS1 to S2, and the precise determination of the event's location in 3D. I realized I had forgotten to set up my video, which I'm doing now. You still see the slides?
Yes, we see it.
So this is a slide with the original warp collaboration. You see here this beautiful fact of nature for the argon-based events. So on the left-hand side, you see the typical trace of an electron when you take the integral of the light, okay? You see the very high ratio of S2 over S1. Compare it with what happens in the left. The ratio of S2 over S1 is reduced. It's only a factor of 10 in terms of light. Here, the output of the photomultiplier tubes is integrated, and it's then decay with a very slow slope of a few microseconds. But if you zoom into the region of S1, what you see here is that the signal for an electron builds up over many microseconds, while for a nuclear recoil, it's almost instant, the rise time. Okay, it's at the level of a few nanoseconds. It's a very dramatic difference, which is very important from a statistical standpoint and provides one of the best, perhaps the best discrimination power in the search for dark matter altogether. So you see here some of the very early and pioneering result of warp in the dark matter search. In this axis, you see on the vertical side the ratio of S2 over S1 in a logarithmic shape. And on the horizontal axis, the pole-shape discrimination parameter. And so it's easy to spot the two differences in the calibration runs between the betas, which are the big blob on the upper left side, and the nuclear recoils. So in the case of the plot in the left, the nuclear recoils are generated with a neutron source. Okay, and if you take away the neutron source, that region goes to 0. It's completely depleted. And you see that the discrimination power is very significant in the pole-shape discrimination. It is less significant in the parameter S2 over S1 because this blob of events has a tail that extends deeply for small values of S2 over S1. So even for electrons, there is a class of events that has ionization suppressed, And this renders the discrimination in the case of argon less important and less powerful for S2 over S1. The very important discrimination tool is the one that is coming from pore shape discrimination. So this was the early warp detector that had been built around 2008 in Gran Sasso. Was operating with a chamber of 150 kilograms with regular argon and had a cryostat that was designed to house eventually a detector that could go possibly to 1.4 tons. And you see the detector being here loaded and being inserted into the middle of the chamber with its side of Vito PMTs here that it's surrounding the internal chamber. And this is the internal chamber of the detector. So the warp detector did not have a good fate because what happens is that notwithstanding the very best attempts to put it into operation, it suffered a series of consecutive breakdown in the high voltage. Okay, those were the years where the technology for the high voltage filters was not very well under control and led to a series of problems in the development of the technology. So eventually we had to rebootstrap the program in a much more controlled way. And this is why the DarkSide program was born with DarkSide 50, which is a design very different from the one of Warp, simplified in order to tackle in an efficient way the problem of the high voltage fit through. You have a smaller detector, which is only 50 kilograms, located at the center of a Vito, which is based on a liquid scintillator Vito, all surrounded by water in a water tank of 1,000 cubic meters. One of the features of this detector is the fact that the scintillator also acts as a very powerful veto for the neutrons that are possibly emitted by the chamber and that are the major background for dark matter. I will spend a few words later on describing the peculiar feature of this scintillator-based veto. But this detector was performed a beautiful run. The active mass is 50 kilograms, but the full detector is filled with 150 kilograms of argon. The most notable feature of this detector was the fact that it did not operate with argon from the atmosphere, but we filled right away with argon that is taken from a very deep underground reservoir from which we extract argon. So it's argon from underground sources. And this has one very big advantage, which is to tackle one of the features of the argon that makes it very difficult to scale for very large masses. Argon, as we said before, has an excellent capability of discriminating nuclear recoils from minimum ionizing events. But one element that makes difficult the search of dark matter with argon is the presence of argon-39. Argon-39 is a radioactive isotope which pollutes very strongly the atmosphere. If you extract 1 kilogram of argon from the atmosphere, the rate of argon-39 is 1 Hertz, 1 decade per second. And that scales with the mass, and it becomes quickly very, very important. It suffices to say that in a 1-ton detector, of atmospheric argon, you have 1 kilohertz of argon-39, a very strong rate. And the drift of the electrons is so slow that it typically takes 1 millisecond to extract the electrons. So it's easy to make the calculation. 1 kilohertz times 1 millisecond, the pile-up fraction is almost 100%. So you have a very beautiful discrimination, but you have this problem of argon-39, which is almost unbearable. This is why one of the objectives of the dark side detector was not only to demonstrate fully the capability of argon discrimination, which had been left hanging from the technical problems of warp, but also to demonstrate the ability to strongly abate argon-39 by using underground argon. So here are the results of warp. First of all, you see here on the plot on the upper right side, a beautiful separation of background from the region expected for the neutrons. The region expected for the neutron is the one with a blue shaded region. The lines that are labeled 50, 65, 80, 90, 95, and 99% are the acceptance regions for nuclear recoils. You see that one can push the acceptance down to the level of 95, 99%, and still you're very far from the background. And this is not a Monte Carlo. This is 20 million events collected with the underground argon. So you have a huge discrimination power. And at the very same time, you have a very strong reduction of argon-39. So the detector was operated for a very short time with atmospheric argon. Have a look at the plot on the bottom right. And with atmospheric argon, we had a very strong content of argon-39. You see the beta spectrum, which is the big bump in the black curve. Okay, that is the beta spectrum of argon-39. And immediately, as we inserted the underground argon, there was a very strong reduction of argon-39 by over a factor of 1,000. By over a factor of 1,000. So the DARSA 50 results really established in a strong way the viability of argon to scale for very large dark matter searches, because you remove the problem of the pileup because you know how to get rid of argon-39, and you have a discrimination which is not possible with the other type of technologies for dark matter searches. Okay, we moved on. This result on the upper right level was obtained with atmospheric argon, okay, with a short run of atmospheric argon to collect a very strong statistic of argon-39. Then the project moved forward to perform a blind analysis over 1.5 years of data. And this was with a process that was totally blind until the end and produced a new result confirming what had been achieved by the Xenon 100 detector at the time, which was a very significant exclusion for dark matter in a region where there were a significant number of anomalies. In addition, the detector was able to produce a very interesting result at very low mass, because at very low masses and a very low energy threshold, in a region where the scintillation signal is not that important because you have a very limited number of photons, but you can rely on the S2 signal. We succeeded in obtaining the lowest background of all, which established at the time the best limit for dark matter below the mass of 6 GeV. Okay. Now, at this moment in time, there has been even more interesting results from the Xenon detector, so that the Xenon detector has the best limit below 3 GeV, and this level this result from DARSA 50 remains the best limit, I believe, between 3 and 6 GeV, if I remember correctly. Before I move forward to DARSA 50, let me spend a couple of words on the scintillator technology. Here the problem was the one of reducing background from neutrons, and there was a very interesting idea on how to approach this. In order to reduce background from neutrons, what we did was to use a scintillator that had a special ability in identifying the signal from neutrons. In other words, this scintillator was not a regular scintillator, but was a scintillator loaded with a significant quantity of boron, the B element, the very light element. Boron has a natural abundance of 10% of boron 10. And this boron 10 has a huge absorption cross-section for neutrons, giving, as a result of the absorption of neutrons on boron 10, alpha particles. So what happens is that, unlike different scintillators where you generate, as a result of the neutron capture gamma particles, you have a flash of light from an alpha which is contained exactly at the point of capture of the neutrons. So for this reason, you have the ability of capturing neutrons and giving a signal exactly at the point where the neutron is captured, avoiding the loss of efficiency that comes from the gamma rays, because some of them typically escape the detector. So it was a beautiful development, very effective, perhaps the best method for vetoing neutrons. And we had to abandon it for future detectors because the local authorities eventually decided in Gran Sasso to force the laboratory to get rid of liquid scintillators. Okay, I will stop here to take questions on this development of the technology, the DARSA 50 technologies for dark matter detection. Let me see if you have any questions. Giovanni Volta.
Hi, I have a question about the photosensors. So you, in the first lecture, you said that silicon PM is the future, right? But DarkSide 50 is using PMTs, and yes. So I'm wondering. I imagine that at the time the silicon PM technology was not yet ready. But my question is, how do you deal with the dark count rate for silicon PM for dark matter search, and for the heat power released for silicon PM? I believe that the silicon PM needs some preamplifier, which is in contact with the liquid argon, right? And I'm wondering, from cryogenic point of view, how do you deal?
So the silicon PMs, you're absolutely right. When we started the DarkSide developments, they were still being developed and they were not ready for use at the time. Now, the warp detector was using just regular PMTs, regular for operation in liquid argon, and they were a nightmare. They were not extremely stable, subjected to discharges and so forth, because of this problem of the resistivity of the photocathode at liquid argon temperature. In DarkSide 50, we moved forward and we used photomultiplier tubes that had a preamplifier attached to their back. And in this way, we prevented the discharges and they were running in a stable fashion for a very long time. Now we are moving to silicon PMs. You will see tomorrow there will be 2 lectures from Alessandro Razzetto. These silicon PMs, the newest one that we've developed over the course of 6 years, at liquid argon temperature, they have dark count rate, which is better than the PMTs. It's no longer a problem. And there are ways to deal with the power. The power of the silicon PMs is actually very small. But there is the electronics that is associated with them, which has some level of powers. But again, following some very special developments, this power is fairly contained, and it's at a level where it can be handled without creating problems of overheating in the liquid argon.
Okay, just a curiosity, is this development internal or with some companies?
So the development is such that the silicon PMs that we are using for dark side, which are one of two major lines of silicon PMs available in the world, are the ones that are being designed by FBK in Trento, and are produced by the silicon foundry in Avezzano, a foundry that was selected by INFM. The second major producer of silicon PMs in the world is Hamamatsu. Right.
But they don't produce the electronics behind, just
no,
right?
No.
The amplifier is homemade.
The preamplifier is, the electronic is totally homemade.
I see, okay. Thank you.
Okay, then there is another question from another colleague of yours. I see a hand raised.
Yes, thanks a lot. So you showed these pulse shapes from electrons and argon, and you showed the magnification of S1s, but it seems to me that the difference in rise time is even stronger, even more prominent in S2s, and it seems that the rise times are the other way around. So for argon recoil, way slower than for electrons. So in principle, I would assume the discrimination power to be even stronger for S2s based on these pictures. Is there physical explanation for this? Or
yeah, in principle, it could be stronger, but the problem is that, you see, unfortunately, I cannot see my mouse if I share the slides in this fashion, but you see here, these are if you see my mouse, these are the electrons, okay? There is little spillage in this axis. In this axis, the spillage is minimal, while in this axis, the spillage is very significant. There is a fraction of the events that behave in a non-ideal way and that have ionization suppressed. So it's for this reason that this S2 over S1 discrimination is limited, is not extremely effective. And the thing is absolutely the same also for the xenon. You can get 2, 3, maybe pushing 4 orders of magnitude with the S2 over S1 discrimination, but no more than that. Because there is a tail of events that have ionization that is suppressed by the geometry of the events themselves. While for the push-up discrimination, this tail is totally absent.
No, I meant the previous slide where you showed the pulse shapes. Here it looks like the pulse shape of the S2 signal from the argon recoil is very different to the S2 pulse shape of the electron. And seems to have a very, much slower rise time.
That is not an intrinsic property of the original event. That is a property of how the electrons are surviving and when they come at the surface, you know, what is if you have an event that is a single deposit, then there is a certain distribution of the secondary scintillation light as the ionized electrons cross the ullage or not. But there isn't any useful information in there, trust me. Okay, the optics is affected here by the fact that the S2 signal for the electron goes into saturation. But when you take everything into account, there isn't a very significant discrimination from the shape of S2.
All right, thanks a lot.
I see a question from Francesco Pop in the chat. The local authorities will allow DarkSide to use liquid scintillator once LVD and Borexino will finish their work. No, the determination was that the era of liquid scintillator at Gran Sasso is over. So there will be no longer use of liquid scintillator. This is why we need to go into another direction for DarkSide and for other experiments. Sartak Chudari, why is the xenon discrimination better at the center? if the background from the walls is a problem, should it be the same for argon, right? At the center for xenon, it's better because the xenon at the center has a lot of self-shielding, and it can shield the radioactivity that is coming from the walls. The same is true for argon, but in the case of the argon, that has a less prominent role, because in the case of the argon, most of the minimum ionizing radioactivity comes from the argon-39, which you cannot fiducialize, because you cannot separate from the rest of the argon. It's uniformly spread inside your detector. Okay.
Just to add to that question, so this self-shielding, is there how do you determine to what extent it is effective? I mean, from center, how far do we go where self-shielding is no longer effective?
Well, so shielding is very important. You can go back to the slides, which I don't have right now, of the previous lecture, and you will see the distribution of the events in 3D in the xenon one-ton detector. And you will see that self-shielding is indeed extremely important, because it can limit the radioactivity on the walls, and it can create a region at the internal part of the detector where the radioactivity is very, very small indeed.
Okay, okay. Thanks.
Thank you. So I would like to take a 2 minutes break to take a sip of water, and we will restart at 9:38, if you allow me.
Sure.
Is that okay for the chair?
Yeah, absolutely. We will restart in 3 minutes.
3 minutes. Okay. Let me get the coffee. We will restart. Are you guys ready?
I think so. Please go ahead.
Okay, so the DARSide 20K detector, which is the next generation detector with the liquid argon and Gran Sasso, due to this problem of scintillator, will not operate in a scintillator bath, but will be operating in a liquid argon bath. So the idea is to build in Gran Sasso an exact replica of the cryostat that has been developed at CERN for the ProtoDune project. That is the object at the center. And the cryostat developed for the ProtoDune project will host the DARSide 20K detector without the use of any liquid scintillator to go in a more green direction. That is the representation of the time projection chamber. As you see, the time projection chamber will have a dimension, a linear dimension of 4 meters, both for the diameter and the height. The main construction element of the time projection chamber is acrylic panels that will build up the chamber. It will be instrumented by optical sensors only on top and bottom. There will be no optical readout on the sides. On the sides, what you will have reflector panels that will bounce off the light. And on the top and bottom, you will have 2 optical planes that will be built of silicon PM-based detectors. And you can see here on the bottom, left, right, a first example of the silicon PM detector developed for DARSide. It's a detector that has a surface of 5 by 5 centimeters squared and is composed of 24 silicon PMs arranged in a series of parallel and series combination to be read out as a single channel. When we started this development 6 years ago, the possibility of assembling a photodetector of silicon PMs over 5 by 5 millimeters seemed to be outrageous, okay? Because these devices have a very huge capacitance, and the noise is driven by their capacitance. And it seemed difficult to go beyond 5 by 5 millimeters or 1 by 1 centimeter. Now, at this moment, we have not only mastered the 5 by 5 centimeters, but we are moving forward in a direction where we build tiles of 10 by 10 centimeters, a very significant surface. This detector has an extraordinary capability of discriminating against background and will be able to cover almost the entire region between the exploration curves of LZ and xenon and tone, which are highlighted in black and green, and the so-called neutrino floor for the dark matter signal, which is the one in light gray. In red and in blue, you see the curves of sensitivity for DARSide 20K, which are extrapolated over the course of a 10 and 20 years run. So DARSide 20K will be probably the first experiment starting after the upcoming run of xenon and tone and LZ that will try to take the sensitivity to the level of the neutrino floor. Okay. And it may be followed by another experiment, which is Argo, which is something which is in development in Canada by the same collaboration that is bringing forward DARSide 20K, which will be even more ambitious. It will be a 300-ton detector that will try to take the sensitivity into the neutrino floor. Okay. There are two projects that are crucial to the success of DARSA-20K. The first one is Urania. As we said before, we need to work with some very special argon target in order to operate this experiment. We cannot use argon that comes from the atmosphere. So Urania detector has the ability of extracting up to 300 kilograms per day from a very special location, a very special gas well that has been identified in Colorado, where the argon has a very limited concentration, only 400 parts per million, but is extremely pure. It's the same location from which we got the argon for DARSA-50. So the INFN has built a plant which is called Urania, which has this ability of extracting up to 300 kilograms per day from this site in Colorado with an excellent purity. And then we're building a purification tower in Sardinia that not only will do an excellent job in removing all the remaining chemical contaminations, but will also have the ability of exploring the active isotopic separation of argon-39 from argon-40 at the rate of 10 kilograms per day. Here you see some more information on the Urania project. It was based on tests performed at the University of Naples on the separation of the gases. We are aiming to get a 99.99% purity, and in the latest iteration, there is indication that we can go to a production rate of 330 kilograms per day. The ARIA plant, on the other hand, was designed to separate isotopes based on a quantum property of isotopes. Their volatility depends even so slightly from the atomic, from the total number of protons and neutrons in the nucleus, from the atomic number. And therefore you can separate these elements. If you have many different stages of equilibrium, you can separate them in an effective fashion. This is a beautiful slide from Walter Bonivento, who's the director of the school that I'm liberally stealing, which shows the difference in technology in the span of 4,000 years. On the left-hand side, we are operating at the two mine shafts in Serrucci, where you see the mining tower. And on the right-hand side, you see an Nuraghi that was built nearly 4,000 years ago, within a few hundred meters. That was one of the early forms of settlements in Sardinia. At the time, there was in Sardinia one of the most advanced civilization in the world. You see here the mining site where we are operating. We decided to operate in a mining site because in order to do an effective separation by cryogenic distillation of these isotopes, you need towers of several hundred meters of height. And so you need towers that are hosted either in a structure like a Tour Eiffel, okay, to be holding up the tower, or you can go directly at supporting these towers against the walls on a mine shaft. And that is what we're doing. Here is what we've built so far, which is a test tower of 24 meters, the so-called Serrucci Zero, which has been operated successfully and has demonstrated successfully the principle of isotopic separation. Some details on the plant, and here the test run that we performed in 2019. And now the work has shifted into the preparation of the mine shaft for the hosting of the cryogenic distillation column, which will be quite an enterprise. The construction of a column of 350 meters of height has never been attempted nor conceived in the world. Here are the modules that are already prepared in the immediate proximity of the SoUC tower for installation. And I have two questions that I would like to address soon. Give me 2 minutes. And here is the detector, which is located at Canfranc laboratory that will test the purity of the argon generated by the area project. So there is a question from Iftikhar Ahmad. Iftikhar, if you could read it out, please.
Hello. So I wanted to ask if there's any problem with using a 1 by 1 centimeter square, say PM instead of 5 by 5 or like a half a centimeter. So is there any problem with this using a lesser 5 by 5?
So there is no problem in operating detectors that are 1 by 1 centimeters, but for a detector like DarkSide 20K, you would bring the number of channels from 10,000 to 250,000. And making a detector with 250,000 channels would be hugely problematic.
Okay, I understand. Thank you.
And so it's to limit the number of channels, the limited number of cables, feed-throughs, and essentially the number also of fans necessary for the detector that is necessary to build larger detectors so that the number of channels is strongly reduced. Is that satisfactory?
Yes, thank you.
Francesco Poppi.
Hi, yes, my question is how do prospects for pure xenon or argon are made? How location to extract this is found?
So prospecting was necessary for argon because the argon, we cannot take it from the atmosphere. And we needed to find locations underground. And prospecting was done by taking, myself, other physicists, other engineers. We equipped ourselves with small bottles initially, and we went out in regions in the Wild West where there were gas wells. It was actually quite interesting because the atmosphere was very much like in the strips of Tex Willer. The environment is really like you see it in the Western movies or in the comic strips. It's really complete desert at 2,000 meters of altitude, so it's quite cold during the winter. And you see these pristine land with these the mountains that are really spent volcanoes, which have been eroded by millions of years of weather activities, and it's a beautiful land. And it's a region where the former volcanic activity had a big impact because the crust is very thin, and you can get gas that comes from the mantle at relatively shallow depth, which gives you the ability of getting some gas from the mantle, which is the location in the Earth that has the lowest radioactivity. So prospecting was necessary for the argon. And it took many years of work going around in gas wells and taking samples to establish the suitability of any given location. Xenon is produced industrially, and xenon is extracted from the atmosphere. There is no sufficient xenon underground, unfortunately. But you can extract it from the atmosphere, and typically it becomes advantageous and economical to extract xenon only from the gas wells that have, only from the plants that have a very strong power of liquefaction of air. Typically, it's economical to do so from oxygen plants that serve the big steel plants. Is there any other question on this topic?
I have a question.
Yes.
So is cosmogenic activation that produce argon 39, right?
Yeah.
How do you transport the purified, the underground argon from Colorado or Sardinia to Gran Sasso?
You need to be very careful because you build up quite a bit of argon-37, which decays quickly. And you need to contain the argon-39 activation. So you have a few weeks of time to transport it underground if you want to be keeping it at a level of purity which is very pristine. So it really is a problem. It's not untractable, but you need to deal with it in the correct way.
Okay, because we are talking about tons, so I'm wondering, weeks are enough for transporting tons of argon?
Yeah, weeks are enough. Weeks are enough for transporting tons of argon. You know, we had a lot of experience, for example, from the Borexino project, in which I was involved, and it was the same problem. You have cosmogenic activation of carbon that gives you beryllium-7. You want to maintain it at a minimum, and so you have, in that case, days to transport it underground. From the place it was distilled, which was in Sardinia, to the underground location.
Okay, thank you.
So I will turn now to give you a very short overview of two experiments that are using the same technology of the TPC for neutrino-less double beta decay. The first one is the NEXO detector. NEXO is a time projection chamber utilizing xenon and utilizing also in this case silicon PMs, utilizing a very interesting scheme for reading out on some strips plated with golden quartz substrate for the charge readout, and very innovative liquid xenon called electronics. Scintillation readout, as I said before, we utilize the same principle of DarkSide, which is to utilize VUV, vacuum ultraviolet sensitive silicon PMs. Low noise and very good radio purity, but strong dark rate, which is somewhat of an inhibiting factor for dark matter searches where you look for very low energy signals, but it's less of a problem for the signal of xenon 136, which is a 2 MeV. So this dark rate is less of a problem in that region, and that's why they can utilize with ease the silicon PMs. They've done a beautiful work in laying out their project and in designing a complete detector with a full estimate of radioactive backgrounds. They have a very strong prediction of the performance. You see the region of interest is the one which sees also some contamination from peaks originated from the radon. So it's very important to have a very strong background control if you want to achieve the full sensitivity in that region. And the projection is that the NEXO project, which is under discussion for funding by the Department of Energy, should be able to essentially cover completely the region of potential discovery of the so-called inverted hierarchy and move into a region that is very interesting also for the exploration of the upper top portion of the so-called normal hierarchy region for the neutrino matrix. They're doing a lot of improvement on the detectors in view of this big decision that is looming from the Department of Energy. And they are certainly one of the big pioneers in background reduction. They have a very, very strong record in terms of being able to examine the material radioactivity and minimize it in order to reduce background altogether. Their scheme is the one where they have this liquid xenon chamber, which is contained in a big water tank. And the liquid xenon chamber is essentially thermalized by a ultra pure fluorinated liquid, also cryogenic, that has a very high purity and serves as a thermal bath for the liquid xenon TPC. Another interesting avenue for the xenon based detection of neutrinoless double beta decay is the next project. Next is a TPC of xenon gas, which is turning its attention in a very interesting way towards the identification of the barium ion. So not only they want to reject background with the use of gas and with the reconstruction in 3D of the tracks, but they also want to prove that actually the xenon had a double beta decay to barium by identifying the barium ion in the xenon target, okay? And this is very important because in this way they can reduce the background absolutely to zero. Of course, the only background that remains is the one of the double beta decay with two neutrinos, which also produces a barium ++ ion. So how this is done is to utilize the usual structure of the Nexo detector for a gas TPC. Gas TPC has the advantage that the medium is less dense and you have two tracks that become much longer. And you can actually reconstruct the 3D imaging of these tracks and discriminate very strongly against background because you have the ability of seeing the two tracks from the two electrons, essentially. But at the very same time, the difficulty of this technology is the fact that you really need to go to high pressure to obtain a significant mass of xenon. And going to high pressure requires the use of fairly bulky containment vessel, which generate potentially a very significant background. Okay, so barium is important because it's a very strong help in the reduction of background. And this group had the very interesting idea of using fluorescent dyes to possibly distinguish between barium ions presence or absence. Because there are some fluorescent dyes that at a single molecule level are affected by decoupling with the barium ion and can produce the excitation level, can produce a response of scintillation light with a single molecule, which is quite a difference depending on their coupling with the barium ion or not. Okay, so you can excite with a laser of 365 nanometers and you see two different colors depending on whether the molecule is in contact with the barium ions that curves it up on its own or not. This is something that goes under the name of FBI, where it's nothing about the Federal Bureau of Investigation, but it's a fluorescent bicolor indicator. And it's a very recent development. And some beautiful R&D has been done by depositing on a silica pellet this fluorescent bicolor indicator, and by using with some atomic techniques individual barium ions to demonstrate that you actually do have this ability of really distinguishing black or white, the presence of barium or not, by detecting the frequency of the light that is emitted by this molecule when it's excited by a 365 nanometer laser. So you see here some of the results of the early phase of development and the difference in the response of this very peculiar molecule and the ability thanks to this molecule, of making a very special discrimination for the presence of the barium ions or not. Clearly, the strong problem is how to do all of this in a detector, which is also the background. And there is a very conceptual scheme at this moment in time, which is the one of having a laser with a motorized system that can perhaps deploy the laser within the chamber and move it around and try to localize the laser exactly where the barium ion, the potential signal from the barium ion is expected, which is where you see a possible candidate of the neutrino-less double beta decay. It's a very complex detector because you need to do that within a low background detector. And you need to do that within a detector that also has to be very efficient in detecting light and charge. And so where the ability to shine a laser is limited by the fact that you need to have surfaces to detect light and charge with excellent quality. So it's a very interesting development, something which is still at the level of conceptual system, but you should look out for the development of the system because it has the ability to zero out, if successful, any other background which is not coming from a double beta decay, either with 2 or with 0 neutrinos. Okay. So with this, I've concluded my perspective on novel liquid detectors, and I've tried to give you a sense of not all perhaps, but the efforts that are most prominent in this decade, so that you can have a chance to have a look at these technologies. And I'm available for questions now.
Thank you very much, Christian. It's a very, very complete and beautiful overview of the novel liquid detectors. Please, questions? There is a question by Francesco Poppi, please.
I'm sorry, I have a question about DarkSide.
Please.
Will DarkSide 20K be able to investigate and maybe give us more hints about the low energy electron recoil region, which was, let's say, which xenon provided very interesting results? I mean, will it be an independent result? Will it be possible, I mean, with DarkSide?
So the signal at the very low end of the spectrum of xenon.
Yes, that was the question.
That one bin that stood out from the background. No,
yes.
We will not be able to provide an independent check in that region, because in that region, the background from their side is limited by the argon-39 at a level that does not make that specific channel in DarkSide 20K competitive with the result of the xenon detector. So in other words, you cannot reach the same level of sensitivity due to the presence of argon-39. On the other hand, that result, which I remind you, it's only a single beam, will be soon probed by the xenon and TON detector. And so we will hear more, and by LZ, of course, and we will hear more about it very, very soon.
Other questions? Giovanni Volta.
I have a question for DarkSide. I was just wondering which are the other physics channel that DarkSide can investigate, like also in this optic of the excess that xenon observe, like axion-like particle, or I don't know.
So the other channels for DarkSide is that DarkSide can serve as a beautiful monitor and a measuring tool for supernova neutrinos. It's going to be one of the most important tools for the monitoring and discovery of supernova neutrinos. And actually, the chair of this section, Davide Franco, is one of the persons that pushed the science, the complementary science that can come out of supernova neutrinos in the most significant way. So that is one important complementary physics aspect of the DarkSide 20K detector. The other complementary physics aspect of the DarkSide 20K detector is the potential for the observation of neutrinos in the region which is intermediary between the boronate neutrinos and the low energy neutrinos. So the neutrinos in the range of P and CNO neutrinos that have been subject of the latest investigation by the Borex-CNO experiment. Above the spectrum of argon-39, that is also where DarkSide 20K can play a significant role. While for the investigation of the low energy neutrinos in the region where DarkSide will be covered by the argon-39 spectrum, this is best explored with the xenon and TOM and most probably with the Darwin-like experiments of a few tens of tons of neutrinos.
Thank you.
Andrea Mancuso.
Hi, can you hear me?
Yes.
Yes, I wanted to ask you something about the time scale of DarkSide 20K.
Yes.
I mean, the construction when it is foreseen and also the data taking.
Yes, we should be up and running and taking data by the end of 2024, beginning of 2025, okay? The construction is about to start. The first requests for civil construction were submitted by Gran Sasso Lab to the civil authorities just a couple of weeks ago. And we are waiting for the start of the construction of the big prototype like cryostat at the beginning of 2022. And we are expecting the detector to be completed by the end of 2024 and to be in data taking by early 2025.
Thank you.
Other questions? Maybe just if it was not mentioned in the previous lecture, that I don't think so. I have maybe a request that is, well, there are new developments on the possibility of mixing xenon inside argon, maybe just briefly showing what are the potential on using a mixed technology. Christian?
Yeah, no, using a mixed technology has some very interesting potential for two reasons. So you can load the xenon into the argon in trace amounts relatively easily. One potential interest of the loading of xenon into argon in trace amounts is the fact that you essentially make all the signals much faster because the singlet and triplet decay times, they get taken over by the xenon dimers. And you make the signals emit the scintillation light in the nearer ultraviolet region. So they become easier to detect because they are no longer at 128 nanometers, but in the region of 180 nanometers. So the scintillator becomes much faster and emitting in the near ultraviolet. So if you load the argon with the trace amount of xenon, a fraction of 0.1%, this system becomes quite interesting as a fast scintillator. The typical application where this project could shine is, for example, in medical physics. There would be a strong push to enhance the capabilities of the positron emission tomography, which is the primary tool for the screening of patients against the most aggressive forms of cancer. The limitations of the positron emission tomography today are the limitations of the crystals, which are the targets for the gamma rays emitted by the capture of positron or electrons, the decay of the positronium, essentially. So the limitations are due to crystals, okay, because the current generation of positron emission tomography machines are already substituting photomultiplier tubes with silicon photomultipliers, so gaining a little bit in terms of efficiency, but gaining a lot in terms of compactness of the machine. But you can do much better, because if you substitute the crystals typically based on lutetium that are at the core of these machines, lutetium-based scintillators, if you substitute them with noble liquid scintillators, you get an increase of a factor of 4 to 5 in light, and you can also reduce the emission time by a factor of 2 to 3, which means a faster, brighter scintillator, and you can gain a lot in terms of having a better system for detecting the gamma rays from positronium decay and reconstructing the position of cancers and tumors in a patient's body. There is also another possibility, which has to do with the loading of xenon at a much higher fraction of mass into argon. Okay, if you can succeed in loading xenon at a much higher fraction of mass into argon, you may have the ability of operating a neutrinoless double beta decay program inside an argon bath at a temperature of 87 Kelvin. This brings two advantages. One advantage, which is important, but in a way also marginal, is the operation of silicon PMs at a much lower temperature. And we have said before that operating the silicon PMs at a much lower temperature gets completely rid, you will see tomorrow in the lectures of Dr. Razzetto, gets completely rid of the dark count rate. So essentially you can kill the dark count rate of the silicon PMs and you can work without that source of noise. Okay. That source of noise is important, but it's not untractable at 2.6 MeVs, which is the Q value of the Xenon 136. The other most important factor of operating a system at 87 Kelvin is that you can actually suppress quite significantly the background that is coming from radon. Radon is a very important source of background. Operating a detector at 200 Kelvin, which is the base temperature of the xenon detectors, has one strong disadvantage, which at that temperature, the radon has a very high volatility and has a very high vapor pressure. So it's very, very difficult to stop radon from emanating at that level of temperature. While if you operate the detector much colder at 87 Kelvin, it becomes much easier to trap the radon because you can trap it with very strong effectiveness on charcoals, on activated charcoals. And you can also essentially inhibit very strongly the emanation of radon from surfaces. So the mixture of argon and xenon has two important avenues for consideration. One is medical physics, where it really could shine and could bring a very significant improvement over the baseline performance of the PET. And the other one is the possibility of operating a neutrino-less double beta decay, which has a strongly reduced background. And you will see here in this slide, okay, that this is indeed very, very important, because unfortunately, when I project the slides in full screen, I lose control of my mouse. But have a look at the plot, which is on the left upper side, okay? And have a look at the plot that shows in the region of interest, that peak, which is fairly prominent, around 2.45 MeV. That peak is dominated by the orange component, which is internal of uranium-238, and by the TPC vessel, which is internal, the uranium-238 in the TPC vessel, okay? And is exactly in the region of interest, exactly where you expect the signal from Xenon 136. So it's this, and of course radon, okay, which also produces a signal in that region. If you were able to load significantly xenon into argon, you could at once eliminate the radon because it gets suppressed by many orders of magnitude. You could also use the fact that you have a very strong mass of argon, in which the radon is diluted, to fiducialize and to eliminate the signal from the uranium-238, which is coming from the internal components and from the TPC vessel.
Okay, thanks a lot, Christian, for this extension that gives us some nice overview of the future of this technology. Other questions to Professor Galbiati also about this last point? Okay, if not, let me thanks again. We have now in the agenda a break for the coffee. It's half an hour before Caroline Schaffner lecture. So if Walter agrees, I think we can anticipate a bit that talk, and also if Caroline Schaffner agrees, and we can restart at 11 o'clock. Is that okay?
For me, it's fine. You have to ask Caroline. If she's not around, she will not know.
Yeah, sure. Yeah, I saw her connected before. Now it's not.
Maybe it's better to keep the original time.
Yeah. Let's keep the original time.
Know that the lesson starts precisely at 11:15. So we should keep.
Okay, sure. I was thinking she was connected, but I agree with you. It's much better and safer to keep the original plan. So let's reconvene at 11:15. See you later. Ciao.
Bye.
Bye. And in the meantime, you have some more time to put your hands on the exercise for the statistics. In the afternoon, we will come back to it. Also, as it is reminded in the flyer on the screen, there is this vote for the best poster of the SoUP school. So you have the possibility also today to vote for it by the end of the day. So please do it. It will be a nice conclusion of the school tomorrow.
Okay, welcome back to the workshop. So basically, we can resume with the lecture by Caroline Schaffner. Caroline, are you ready to share your screen?
Yes, hello again.
Hello.
Let me try to share my screen. Okay.
Yes.
See it full screen?
Now, yes.
Yes, okay, great.
Okay.
Good. So yes, so hello everybody again. This is the second part of the solid state detectors. Last lecture, we stopped more or less when after the introduction to what different kind of detectors we have. I put a bit emphasis on the temperature detectors, as maybe this is something less known in general. Then, we started out with looking at experiments and the results in direct dark matter detection. And today we will also then add the neutrino double beta decay searches. And just to get us all back to the last status is, I'll show you again here this picture where we have the different detection channels we can look for in this detectors for direct dark matter detection. The important thing is to realize that, so if you just detect one of these channels, for example, just the scintillation light, you don't have particle discrimination. Instead, if you detect like scintillation and ionization, as you have heard today by Cristiano again, there's a way of discriminating nuclear recoils from this common background, which is interesting for this standard wind dark matter searches. And just a brief overview on what we will look here in that lecture. There is the scintillator experiments, which are like DAMA or DAMA-like. Then there is ionization, pure ionization detectors I will report you about with CDEX and also this skipper CDs if we have time. Then there is dual channel readout of heat and ionization by this cryogenic semiconducting calorimeters. Consisting of germanium and silicon by super CDMS and Edelweiss, and the scintillating calorimeters measuring heat and scintillation with CREST and cosinus. Again, these experiments, they're underground. They're distributed more or less and spread over all the underground labs we have in the world. And just a brief reminder, so the solid state detectors, they have good performance in this lower dark matter particle mass regime, so below a couple of GeV reaching down. In this sector here, where you see all these blue limits, they are from xenon and other liquid noble gas experiments. So they are experiments which can have a large exposure now in the ton and n-ton scale, so they can acquire a lot of exposure, and this gives them then sensitivity moving here downwards. Whereas if you want to move here to lower masses, your detector also has to have a low energy threshold. So in this region here, there's there's quite different technologies, and also mainly the solid state detectors. And you see, in sensitivity, there's quite some orders of magnitude in between, and we will see also from all these experiments. So they are typically small experiments running a couple of detectors with a couple of kilogram maximum, whereas here you are at the ton scale, which you of course need if you want to go down. But also the solid detectors, they have now there's this vision to arrive at sensitivities in order that you can explore down to the neutrino floor. As I said, also, yes, there is no signal so far, apart from DAMA Libra, which if you plot their result in this standard scenario interpretation, you get these two islands here, which is for sodium and iodide, because it's a two-compound material. And you see there's this huge discrepancy between the null results of more or less all experiments and the DAMA Libra result, which is something the dark matter community is working on clarifying. This was also what we started out with then, so this modulation searches, and I reported to you about DAMA again. So this is a really like a big mass experiment with 250 kilogram of the sodium iodide crystals. And here again, there is their results. So you see this modulation observed in this phase 1 and 2 with high significance, and they claim that this is the evidence for presence of dark matter in our galactic halo. Yeah, so the signal of Dharma, again, so it's this high statistics, period and phase fit to a dark matter interpretation, and there is no convincing other explanation so far. So this is why actually there is this effort now in getting experiments that have a sensitivity running to cross-check Dharma, and this is really something the community is even now pushing and investing money. The question why this is interesting comes from the fact that this comparison, or better say the cross-check by the other experiments is done at least with different targets. So if you again look at this per recoil rate, so you see you have a part here where the dark matter nucleus cross-section goes in, and here you have a dependence on the form factor, and which comes from the nucleus you have in your target. And this target dependence in the end is the reason why you would like to do a sodium iodide experiment, and why you say, okay, it's not just fine to check this now with xenon, calcium tungstate, germanium, silicon, and so on. So the idea is really to do a model independent cross-check using the same target material. The experiment which are, let's say, on the market and trying to do that is quite many now. So there is anice, which I will start out. Then there is cosine. This is in Korea in the Yang lab. And then there is SoUP and cosinus, which are transaxle. And SoUP has this special feature of having also an experiment on the southern hemisphere. And there is also DMIs, which I will report about. Okay, as said also, end of last lecture, what is actually, what you should have on your list if you want to do such an experiment, is that, the threshold should be comparable to the experiment you want to check, of course. Very important is also the background level of the crystals employed. So they should be also rather low, best as low as Dharma, which has 1 count per kV kilogram a day, in particular of this potassium. Because in the last lecture I showed you that they observe the modulation in the energy region between 1 and 6 kV. And there's this background contribution from the potassium, which makes an electron capture, and you can have this 3.2 kV X-ray, which comes from this isotope. And this is, of course, something you should have under control, because if you would have their huge contribution, this would kill your sensitivity. Also for a modulation search, it's not enough to have a 100-gram detector, so you have to have quite some order of 10 kilogram or 100 kilogram or more. And if you want to do a bit more than what Dharma has, of course, you can think about suppressing this potassium with a liquid scintillator veto, as I will show you in a second, and also add a muon veto, which Dharma, for example, doesn't have. And if you would want to change, maybe even detection technology, particle discrimination would of course be something very interesting, because Dharma measures this energy spectrum, sees this modulating rate, but they cannot tell you if this is now due to electron scattering or nuclear recoils, or so there's no information actually on this interaction channel of this events which modulate. Okay, so let's start out now with anice, which is an experiment in the Canfranc underground lab in Spain. They have 112.5 kilogram of sodium iodide crystals. As Dharma, they measure the light. So you see here also a crystal of them, which they have it's housed in a copper cylinder. And there's also around the crystal some Teflon for better light collection. They, as Dharma, don't have any background discrimination, so this is in this case the same. The threshold is around 0.9 kV electron equivalent, so a bit lower than what Dharma has achieved in the second phase. And they are in data taking since August 2017, so almost 3 years now. They have also a muon veto. And yeah, here you see, yeah, here you can see their setup. So yeah, in the most inner part, there's the crystals with the phototubes. Then they have some high Z material around with lead and copper. This all then is closed up in a box, and this is flushed with nitrogen in order to avoid to have any radon contribution, which is also important. Here you see also a picture of that. Here they have also some access to the crystals where they can insert calibration sources. And then, yeah, they have here some active veto panels for muon tagging. And then in order to reduce also the neutron background, here some yeah, polyethylene shielding put around. Here you see then a picture of how this looks in reality in the Cannes-Frank lab. So it's a rather small setup in comparison to, I guess, what you have seen before to this, yeah, like dark side or other experiments. Genau. So what about light collection? So they have very high collection of around 15 photoelectrons per keV of all the crystals. So this is very good. And the threshold, as I said already before, is lower than 1 keV electron equivalent. If you want to compare this now to DAMA, so they had in the first phase around 5 to 7.5. And then 6 to 10, so there's quite some difference. So they are really doing good in light collection. So how they calibrate and how they know that the threshold is 900 dB or below is thanks to internal contamination. So they are normally a pain, but they can be also a benefit if you want to do low energy calibration, because yeah, this is actually a big trouble, because if you want to have some hundreds of EV or keV calibration line, you have to really have it close to your active detector. You cannot shine from it from outside, because this detectors you have seen, they're always housed in copper containers, because the sodium crystals, they're hygroscopic. So you typically have a lot of stuff around them. So if you want to really do a low energy calibration, it's quite tricky. So you have to have some access, which of course it comes always with problems. And also you can introduce radioactivity, you can harm the crystal because they are hygroscopic. So in the end, it turns out to be also quite a nice feature of this SoUP2021 isotope, which makes an electron capture, and you get a high energy gamma and this X-ray. And so if this happens in the crystal, you can on the surface, so this gamma escapes, and you see here then the 900 eV, and this is some data fitted of their detector. And the same is true for actually the decay of the potassium-40, where you get 3.2 keV, so shear electrons, where you can see here the peak. So this is then very nice, can very nicely also be used for calibration, of course. Okay, so to compare a bit now their sensitivity to DAMA. So here you see the background spectra. So in blue here is the data. So you see here some decaying. Then there's the 3 kV bump, and then okay, it goes on. Here you have then the potassium contribution, the polonium contribution, and the overall counts per kV kilogram a day is around 3, which is factor 3, a bit more higher than what DAMA has, with 1 count per kV kilogram a day. So this is also shown here. There you see 1 kV, 2, and what they achieve. And on the next slide now I'll show you so we have to see the energy range. So this is 1 to 6 kV here, and this is then 2 to 6 kV, and this is now the rate versus the 3 years of data taking time of the 9 detectors for the 2 energy regions. And you see also a fit to that with a null hypothesis and for the modulation. And if you have a closer look now at one, again here in blue, in red the null hypothesis, and in blue for the modulation. And in green here, there's also put on top the modulation Dharma sees. And yeah, so their results from the last 3 years, they are incompatible with Dharma, so they don't see the modulation. So this is shown here. You see the modulation amplitude of Dharma and the one by Anais. And yeah, so the sensitivity is 2.5 to 2.7 sigma. And yeah, so this is the result they achieved now with 3 years of data taking. Their detectors, which have a slightly higher background, because the crystals is not as radio pure as the Dharma ones. And of course, they have a less target mass by a factor of 2. And this is what they achieve. Then there's an experiment which more or less started at the same time. It's called COSINE. It's in Korea. They have 100 kilogram of sodium iodide, out of which but 60 are used now for some dark matter search. They measure also the light only, so it's just the same. They have a slightly higher threshold, and they started in September 2016, so a year before Anais. They have also something different to Dharma, as they have a liquid scintillator veto and also a muon veto, which I will explain in a second. So here you see a picture of their setup. Again, just the sodium iodide crystals in copper containers paired with the phototubes. And yeah, here you see a photo close to such a crystal, which has quite good optical quality. And yeah, so their setup is shown here. So we have inside, again, the crystals. They are immersed in a liquid scintillator. And the reason for doing that is to tag, for example, this potassium background. I show you in a second. Then they have outside also passive shielding, and then they have also muon counters again. And yeah, so this is pretty similar to what Anais has, but in addition, there is this inner scintillator veto. Yeah, just also a few words on how many crystals they have. So they have 8 of these shown here. The overall background is 2 to 3 times higher than the one of Dharma, so it's similar to Anais, and they also have a high light yield of around 15 photoelectrons per keV. And yeah, this is where they are located. I thought I show it because it's nice to see where such underground labs can happen. So there's a power plant. You see here, they have here water, and they let this fall down and produce energy. And then, of course, this is like you have to go in there. So there's also the possibility to make another hole where you can, for example, then do some physics experiments. It's a bit scary because if you think about there is some problem, but yeah, it's another way of doing underground labs. And yeah, here now the explanation to this veto. The end you have inside here your crystal, and then if you would have now this decay where you see the 3.2 keV Auger electrons, but the gamma escapes, so you don't see it because it happens on the surface, for example. This would then be detected in this scintillator, liquid scintillator veto, and then you can, of course, just take it, subtract it from your data. This is shown here. So in this way, you can reduce this background by quite a bit. Here they show also their energy spectrum. So you see here the data, and also fit with their Monte Carlo to describe the background. And you see the different contributions from the background model. And so the rate here is around 2.7, so it's a bit lower than what Anais has. What is their result so far? So they published in 2018 some spin-independent search results where they simply, so they don't consider modulation in that case, but they just do a cut and count experiment. So they have their background model, describe what they see, and then try to fit a null hypothesis and a WIMP. And what they then get here is a limit which you can then do for the standard scenario. And you see that they exclude actually both of this Dharma island. So this there was a lot of noise when they published this. But in the end, I mean, it's not so exciting because, of course, also all other direct searches already excluded Dharma in the standard scenario. Of course, they have a different target, but it's always in the standard scenario, this was excluded already. Shortly later, they then also published some modulation search analysis. This is shown here. So you have here, again, this modulation amplitude and the energy. And you see here, you have to have a close look. So there is in light blue Dharma, and dark blue also Dharma, phase 1 and 2. And then in red, you would see their single hit events. This is the interesting part. And you see, okay, there's far bigger error bars and also not as low threshold. And yeah, when you look at all the crystals, so you see again this decaying rate. This comes because there's some radioactive isotopes which decay during this 3 years also of measuring time they have. And yeah, if you do then on best fit, this is what they see. So their current result, it agrees both with an null result and the Dharma one. So there is not more to say on that, but they will soon publish. This is what I heard. So soon there will be also some update from their side. So yeah, to summarize, I mean, both of them, Anais and Cosine, they run since 3 years. Anais excludes now Dharma, and Cosine, agrees both with the results and the null hypothesis. And yeah, so there is still the question is open. Then a brief also information on what DMIs is. So this is also a sodium iodide search at the South Pole. So there's this ice cube, big ice cube detector you for sure all know. It's really cool. And yeah, on one of their strings, they put then also on, they put then also on sodium iodide crystal. So they just hang this like a couple of kilometers deep in the ice. And yeah, it's paired with 2 phototubes. The threshold is rather high, so it's around 4 kV electron equivalent. So there's a factor of 4 now to Dharma and the others. And yeah, they took data in 2011. And what is special about them is, of course, that they are on the other hemisphere. So if the Dharma signal would be due to some seasonal effects, like related to neutrinos from the sun or similar, which is not so obvious and also not supported, but still, if you would like to check for this kind of things, it's of course very interesting to do and search on the other hemisphere. And here you see their rate versus energy. So they have a quite high contribution from the potassium, and they have here then also quite some background. The total exposure is about 60 kilogram a year. So if you run only one detector, you see getting exposure is really hard. And yeah, with this data, if you do this modulation amplitude, you see Dharma again in blue, and this is the 2 detectors they have, green and red. And yeah, you see that they cannot do too much on giving a hint if now Dharma, they confirm or reject what Dharma sees. So they plan also to upgrade that, but I don't have more information than this on that topic. Okay, so now you can of course ask, so what is next with the searches on the modulation? And there's quite some more aspects to it. So Anais and Cosine, they run, so they just go on running and accumulating more statistics. And yeah, actually Anais, so here you see this the real time. And you see after the 3 years, they stay very much on their predicted sensitivity. So this was data releases they did. So now was year 3, and they, you see when they are in year 5 to 6, they will pass this 3 sigma line. And this is also the goal for the moment for both of these experiments. So there's not too much to do than waiting. And so there was I was participating to this Morion workshop this year, and there was also Susan from Anna is giving a talk, and yeah, so there was then coming up the question, so how to explain the Dharma Libra positive result. So if the experiments that use this target like Anais and Hussein, they don't find the modulation, is there other explanations to that, or is this then another contradicting result? And yeah, she mentioned the quenching factors, which I appreciated a lot, because this quenching factor is very important, because you know the crystals, the scintillation output for different particles is different. So you have a nuclear recoil produces less light than an electron or a gamma at the same energy, and this comes in with this so-called quenching factor. And the quenching factor for sodium recoils. So if you have, for example, a dark matter particles hitting the sodium atom and doing a recoil, and you would expect a factor 0.3 of light only in comparison to a electron recoil at same energy. For iodine, as it's even heavier atom, this is even lower, and for Dharma, they said this at 0.1 roughly. And then there was a lot of measurements done of this quenching factor, so you can bring a crystal to an accelerator where you accelerate some atoms, and then shoot maybe on a hydrogen or a lithium target to get neutrons. So you in the end bombard your detector with neutrons, and by the scattering, the elastic scattering, you know the energy, and then you can determine this so-called quenching factor even in dependence of the energy. And here you see results of different groups done in the years from the 90s to a couple of years ago, and you see that this is here all for sodium. You see that the tendency is that they are rather lower than 0.3. So here you see 0.3, and most of this results, the one here of cola also, I mean, it's even below 0.1. So this is rather worrying, because a change in the quenching factor translates directly to the energy scale, because if you say, like in Dharma, if the crystals there have a quenching factor of 0.3, and you compare this then to, I don't know, Anais, which I'm just guessing has a quenching factor of 0.1, there's a factor 3 in the energy scale. So with the same threshold, you see then by a factor 3 less than what the other one sees. So this is very important to look in, and as there is no way to do an in situ neutron and quenching factor measurement in such Dharma and Dharma-like experiments, you have to do this at the facility, but you have to be sure that the quenching factor that you have for your crystal is tested with your crystal, because if there is a variation coming from crystal properties, for example, by the thallium dopant, this is also something I'm involved myself. So we are doing now in August a measurement at Tunnel, which is a scattering facility where we will test crystals which have a different amount of thallium dopant and check if the quenching factor varies depending on how much thallium, for example, you have. So just as a reminder, this thallium, you put in this sodium iodide to have scintillation centers such that you get higher light output at room temperature. So just to mention that, so this is a very important point, and has to be clarified also to then answer what we actually do and think and how we go on once this Dharma-like experiments confirm or not confirm Dharma. What else is also going on is, like we mentioned, another 2 sodium iodide experiments which are presently in the construction phase. So there is SaPre, which is an experiment which will run 50 kilogram both in the northern and southern hemisphere. They are at the moment running, or did run a proof of principle detector, and they have also muon beta scintillator Vito as cosine plus these 2 sites. Here, I show you where the other site is. So one is in Italy, as I said, and they're located in Hall C at the moment, where there is also Borexino, for example, and there we go dark side. And here is the other side, which is in Australia, close to Melbourne, in this Stowell lab, which is a new lab. They're building it new, and it is inside a nickel and gold mine, if I remember correctly. So this is a minery where they now are also like creating space for the experiment. Here again shown why this is interesting. Of course, if you have some seasonal effect, this should be just antiphase to if you go to the other hemisphere, but not for the dark matter. So this is one nice feature of this experiment. The other nice feature is that they are working on getting very, very clean crystals. The goal is cleaner than the one of DAMA, which seems to be an easy goal, but actually it's very hard. And we also see that like COSAN and ANAIS, they don't have the same level of radio purity as DAMA has. Here's a sketch of their setup. So there's again a vessel which is filled with scintillator. Inside is then the sodium iodides, and outside there's a huge neutron shield. Here you see one of their crystals. So they have two prototype crystals grown in the collaboration. And yeah, they have a hexagonal shape. And yeah, so here you see the effect of the veto. So if you tag this potassium, which is still in, you can reduce quite a lot or reject this background by here 84%. Genau. So here is the result that their feature of having a good crystal is actually true. So you see here the energy spectrum where they report ANAIS, which is the pink one here, COSAN with the stars, the black one, and SABRE and DAMA is this red and blue line. So you see they are there where DAMA is, or even below. And yeah, so this I would say is really great, and it's a lot of effort. Now they of course have to produce more of that crystal, but this is a big achievement, as in the last decade it was not possible to produce crystals as clean as the one used in the DAMA experiment. And of course it's a problem as long as you don't have such clean crystals, it's difficult to do an experiment. Then I would like to mention Cosinus, which is the project I'm also involved in. It's a new project. It's completely different to the other sodium iodide searches, as it doesn't do a scintillator experiment at room temperature, but it's a cryogenic experiment measuring the heat signal and the light signal. It will be installed at LNGS starting in September now. And thanks to this double channel readout of heat and light, we can do particle discrimination. So we can decide, yes, this event is a nuclear recoil, or no, this event is an electron scattering. The threshold goal is 1 keV, both for nuclear recoils and electrons. So there is the heat signal is not quenched, so it's independent of type. So this is also a bonus. And some more details on the technique. So as I have shown you in the first lecture, so we have this cryogenic calorimeters where we have the absorber crystal. So in this case, maybe sodium iodide. It's paired to what we call a carrier crystal, where there is then the transition edge sensor deposited on, and this is all brought below 10 millikelvin. And if there's an interaction, this heat signal is independent of the particle type, and therefore allows you really to give a precise measurement of the energy of the interacting particle. Then in addition to the phonon signal, also a small percentage of the deposited energy is emitted in form of scintillation light. And this we detect using what we call a silicon beaker. So this is like an espresso cup beaker made out of silicon, where we also have produced a transition edge sensor on. And then by measuring both the light and the heat, you can then do this particle discrimination, because the light output depends on the particle type. The sensors we use is, as I already said, this transition edge sensors based on tungsten. This is a technology which was developed by the CREST experiment here at the Max Planck Institute in Munich in Germany in the last 20 years. I will also tell you later about CREST, which is a low mass dark matter search experiment. And yeah, Cosinus is in this sense a spin-off of CREST because we use the same detection technology, but pair it with the sodium iodide crystal, which is a different target than CREST uses in the past and also will use in the future. Here's just some simulated data for 100 kilogram days of exposure. So here you see now the light yield. So this is now the ratio between the light and the heat, the phonon signal. So typically you would get, like if you would plot light against heat, you would get event distributions like with different slopes, which are different particle types then. If you do the light yield, in our case, this is just this ratio. So your bands with the slope become horizontal bands. And this band here around the light yield of 1 by definition is now the events from beta gamma interactions here. So here for the simulation, we assume an 1K count per kV kilogram and day background plus the 600 microbecquerel per kilogram of potassium, which the Dharma crystals have. So therefore you get here this 3 kV line also. And then, we can here also indicate the regions where we would expect recoils due to sodium and iodine. Of course, this position again here of the bands depends now on the quenching factor that you should determine for the crystal you have, such that you also know in which region you have them. In such a cryogenic detector, you can but also calibrate it, so there is no problem. You can put a neutron source close to your detector. Okay. Ich habe vorlesen, ja. Servus.
Ich höre es adapter. Auf den Plan.
Okay, sorry for that. So there is there's this bands, and then you can hang in a neutron source and then look where you get your recoils of sodium and iodine. This you can also combine by a simulation, and in this way you actually can do an intrinsic neutron calibration, which tells your quenching factors and the area you should look for nuclear recoils in your detector. Here in gray shaded area, I indicate, so actually the modulation signal Dharma observes in the 1 to 6 kV energy region. So you see here, they have the threshold is 1 kV electron equivalent. So you have to put in there the quenching factor. And if you assume now 0.3 and 0.1, this is where all the Dharma events would lie. And you see with such a low temperature detector, you can gain in threshold a lot. And here would be just some simulation of dark matter events, assuming the standard scenario. So this island, this parameter space for the Dharma islands. And you see this is what you would expect then in this 100 kilogram days. So this is really many events, and you see the lower you get, of course, in threshold, there's this proportionality, the more you get. So this is just to show you the difference now between room temperature scintillator experiment and some cryogenic experiment with the same target. Here's some pictures of how Cosinus detectors look like. So they are very tiny and small in comparison to this Dharma-like searches. So you have here around 100 gram sodium iodide, which is attached here. You see the interface to the carrier. And then here the module is closed up with this silicon beaker. And you can also see here this transition edge sensors. So why this is appealing to do, and why also we got financed on that, is that you can with not too much of exposure, which you can accumulate by just 10 of such detector modules I'm showing here. So you build 10 or 15 of those and you run them for a year, and then you can already say with not too exotic assumptions something on the Dharma signal. If you want to really in a model independent way rule out their signal, we have to run about 2.5 years to accumulate 1,000 kilogram days, but then 25 detectors to really rule them out or confirm them. So Cosinus is in the construction phase, I would say. So we have quite exciting moment because we got approved by LNGS. We will build in the hall B. So here you see the xenon tank. So I was standing here on the tank, and then you see the space here. This is now dedicated to the cosinus experiment, and in the back here you see the lunar experiment. There's a rendered 3D drawing of how our setup will look like, just a couple of more details. So yeah, we will have a water tank for the means of shielding against ambient radiation, but also for tagging muon-induced backgrounds. Then we have here what we call the dry well. Here where we inserted the cryostat. Here down is also some clean copper shielding to shield any kind of background which would come from the dry well itself. And yeah, the cryostat is then lowered in there once the detectors are mounted. On top here, there's a clean room. And next to it, we have an utility area where we have some detector mounting space. There's a control room for shifters during data taking, and there's an infrastructure room for the pumps and compressor of the cryostat, because I guess as you learned yesterday by Carlo Bucci, to run such a cryogenic facility, you need quite a lot of stuff, and it's also not too easy, let's say. Okay. With this, I would stop for the modulation searches and continue with low mass dark matter searches. I don't know if there's a question to what I just said. Maybe it's a good.
I see a question written in the chat by Giovanni Volta. I don't know if Giovanni want to.
Have to just a second.
To say by voice, to ask it.
Yeah, sure. I was just wondering if anyone ever thought to move DAMA outside from LNGS, and also is DAMA going to be decommissioned at some point, and the crystal can be used by someone else?
Yeah, so this is a very, very good.
I don't know if in the audience there is someone from DAMA, but
I don't know if Riccardo Cerulli is connected. He's from DAMA. I think he was the chair last session, but I don't know if he's there. So I mean, I can also try to answer. So yes, so there was.
You have muted yourself.
Okay, sorry. Yeah, so there was more often the idea, of course, to move DAMA to the other hemisphere. But you have to imagine if you run an experiment and you have this result, you might consider moving not as the best option. So I guess this is why so far it didn't happen. They are also still running. They go on. You can, of course, also say, well, 12 sigma, it's enough. What you want to do more, you cannot do more. They nonetheless plan also an upgrade, also I think to use the silicon photomultipliers to even do better. About your other question of sharing crystals, this is also something which came to my mind, because I thought, okay, they have so many and they have done their job, right? They could maybe give some to others, in particular as the market is not having such crystals that you simply can buy. But this was also so far not done. So in the end, I guess there is this contradicting result, which I think the only way to seriously solve this is do another experiment. And in the end, the experiments had to go through this effort of producing now radio pure crystals. Maybe I can share with you here also that so for cosinus, for example, we started a collaboration with SICAS, which is in Shanghai, a big company for ceramics and crystal production. They, for example, produced also this 1 ton of tellurium dioxide crystals for the core experiment. So they have experience with low radioactivity and all this requirements we have, which typically the whole world doesn't need. And they produced for us, for example, 2 3-inch crystals of about 1 kilogram each. And they have a potassium contamination, which is 5 to 9 ppb. And DAMA has less than 20. So this crystal is also cleaner than what DAMA has. It's, of course, small crystals. So for cosinus, we don't need this huge crystal. So in this sense, I mean, there's also a difference between producing something clean small and producing something clean big. But yeah, so it seems that there's now more crystal growers in the world which start to be able to again produce crystals as good as the ones of Dama. So I hope this relaxes also in the future, then the situation such that experiments can just get clean crystals and do their science. Yeah, I don't know if this answers now your question.
Yeah, thank you.
Yeah. Some other questions, or shall we continue?
Any additional question? No, okay, I think we can continue. Thank you.
So yes, so the low mass dark matter searches. So as I showed in the beginning, I mean, in this limit plot, so this is a part, this is all the left part of this plot. And oops, okay. So there's one experiment I want to tell you about, which is CREST. So this is also located at LNGS, has different kind of materials in operation. It's calcium tungstate, silicon, and sapphire. There's also, I'm missing here in the list, lithium aluminate. And yeah, they measure, as I've shown you for cosinus, light and heat, using also this tungsten-based transition edge sensors. As cosinus, I've shown you they have gamma discrimination between beta-gamma events and nuclear recoils. They have very low threshold as detectors around 30 electron volt. And yeah, the run, which is ongoing at the moment, started in 2020. Yeah, just to show you here, this is a calcium tungstate crystal showing how to scintillate. And yeah, so there is some more information on the target here now. So these crystals, they are rather small, 20 by 20 by 20, so they weigh about less than 30 grams. So this is really small detectors. The light detector is shown here. So you have this as like a wafer, and on it you have then the TS sensor. They have also very good performance of, so the RMS of the baseline is 2 electron volts. So this is really good light detector. So it's not a single photon detector as you have with the PMT or this other photodiodes, but for being a macroscopic object, they have a very good performance nonetheless. Yeah, here you see it in big. So how this detector looks like, it consists of more than, I think, 150 parts or so. It's really nasty. Here you see the sensor, so it's quite big tungsten film, and then here's this photon collectors. Then you see some holding structure here. There's the sticks which keep the crystals in position, and then this is also surrounded by reflective housing and then closed up with this very clean copper, both for thermal radiation shields, but also for radioactive radiation shielding. Here you see now a result of one of these detectors in this light heat versus energy plane again. So you have here this band due to beta-gamma interactions. And then here you see now this is data from a neutron calibration. So this is actually what I told you before. And with these detectors, you can just hang in a neutron source and then see what the detector response is. And yeah, you see here, so this is due to oxygen recoils and tungsten recoils. The calcium recoils would be in between, so you cannot resolve them. But it shows you that with such a multi-target compound, you can even then study shapes, because you thanks to this light, at least at higher energies, you can really distinguish between the different kind of recoils that you get. Then here some more of this data. Yes, so this detector, the threshold of 30 eV, as I said before, and yeah, the region of interest is this yellow shaded region here. So it's this half of this oxygen band then going down. So you look for nuclear recoils, of course. And if you plot this now in a histogram, you get this here. So you see it's really few events only. So this was running for quite some time, but yeah, detectors are small and rate is low. So you have then here some activation lines, which again, as for also GANAs, they are helpful for doing energy calibration. And yeah, down there you see then a rise in the event rate. and this starts around below 200 electron volt. And if you have a closer look to that, you see, this is quite a steep rise. And if you look then at different detectors at this really low energies, you see they have all a different shape and a different rise, so they're not really compatible, and also the rate is quite different. So because in the beginning, of course, if you see something like this, you can say, well, could be also maybe dark matter spectrum should be flat and featureless, right? And so who knows? But if you then look in details, you see that this is rather disfavored to have a dark matter origin. Of course, then the question is, what is that? Because if it's a background, it's of course also it's challenging and problematic, because you need a way how to describe this background. And if you want to do an observation, this is mandatory. I mean, if you don't have a background model and a complete understanding of your detector and the detector physics, it's really difficult to do some physics then. Nonetheless, you can of course draw a limit, and this is what Chris did that time. So this was back in 2019, I think. And so you see this red line here. So this was the first time this parameter space actually was entered. So this was really unprecedented at the time, and a big success, and also triggered quite a lot this interest in this low mass region. You see this extends down to 160 MeV, and of course, another nice feature of CREST is that you can have different target materials. So this helps, of course, in case you would have an observation, you can look for the spectral shape information and so on. And of course, but there's this, what I just said, the problem of this low energy excess studies, which are ongoing and which are really critical for this kind of experiments. And another experiment in this direction is Edelweiss. So it's at this LSM, so Modane in France in the lab. They run also cryogenic detectors, but based on semiconductors. So they don't measure heat or phonons and light, but they measure phonons and ionization. The detectors is shown here. So you have a big piece of germanium, 800 gram. On that you have a temperature sensor, which is an NTD thermistor in this case. And they have then this electrodes that you can see here in order to apply a voltage. A very important point is, of course, by this two-channel method, you can again discriminate electron recoils from nuclear recoils. And what they also have stated here is this heat-only events. But a very important point is that once you apply a voltage here, these drifting charges, they also produce a larger phonon signal by the so-called Neganov-Tominov-Luke effect. And this is, of course, good because it boosts your signal. So you can use this for getting lower energy thresholds, which in particular now that experiments of this type look for always lower dark matter masses, as this technology also allows for low thresholds. This is good, but the electrons recoils, they are more amplified than nuclear recoils. So in the end, there is similar to the light, there is so-called quenching, and this you have to very much care about, because otherwise, of course, you have a wrong energy scale for the nuclear recoils in comparison to electron recoils. So this is just take it as a take-home message. So always keep in mind, quenching is a very, very important thing here. Quenching is maybe not the right word, but one should care about the energy scale for the particle. Here's some more information on these detectors. So 800 gram, more or less, is each of them. Then you see here they are kept with this Teflon clamps in this copper frame. There's here some bonding to make electrical contacts. And they run, as I said already, in France in a setup which is also surrounded by passive shielding. Here I show you also why they do this with this electrode. So in the end, yeah, it's good for measuring, of course, the ionization signal, but also with that kind of arrangement they have here for this detectors, you can do some kind of federalization. So you can, yeah, in this way, at least discriminate to a certain level surface events, which is good, like alpha n or similar stuff. And yeah, here you see this is something like would be like a fiducial volume of 75%. So this is also a nice feature of this detectors. And here you see them mounted. I think they have 15 here put of this almost 1 kilo each. And this is, yeah, this is the cryostat where they operate them. They have thresholds 200 eV electron equivalent, and for the phonon, for the standard type 500 eV. And yeah, this gives very good results in this 5 until 5 or so GeV. This is very successful also. Then there is also, of course, the trend in this group, Edelweiss, to go to lower thresholds. And yeah, as I told you in the first lecture with the cryogenic detectors, the heat capacity is important driving factor. So if you want to get low in threshold, if you decrease the heat capacity by decreasing the size of your crystal, you can already gain. So you see here the crystal they show here is a 33 gram germanium. And yeah, this has here you see at 43 EV. If you apply this voltage, you can have a very good energy resolution. So this is really amazing. And yeah, so this is a bit the direction the experiments go. So they move from this rather big bolometers of a kilo to now below at least 100 gram detectors with the goal of having a very low energy threshold. So a picture. So here's again the NTB and you see the electrodes. And yeah, with that, they arrive here, exploring masses down to 45 MeV, also using the Smigdal effect, which is also used for the liquid noble gas detectors, as I guess Christiana also told you. And yeah, so they, like CREST, but also observe this excess. So there is events which appear going close to threshold, which yeah, have quite a high count rate. They're also not, they're decaying. So this is also true for CREST. So they have some kind of time distribution, which however doesn't fit to any of this known radioactive decays that are present in such searches due to the materials that one uses. The pulse shape is completely fine with normal pulses, so you cannot discriminate nothing. Yeah, they're also not compatible with any other backgrounds or have some coincidences. So they are just look like normal particle events. And yeah, they of course, as for CREST, they are a problem, and the origin is so far unknown. Then there is another experiment, so the pendant to the Edelweiss experiment, which is called SuperCDMS, which is an American experiment. It's the same detection technique. So you have, again, germanium or silicon. You apply as well for a temperature sensor. In that case, it's not the NTD, but it's also a tungsten TS, so like CREST uses. But then you have also a charge readout. As I said already before, one has to take care about the energy scales. And yeah, the TS sensors they use, they are not with a transition temperature as low as the one of CREST, so 15 millikelvin, but rather 90 millikelvin. So this you can do by yeah, the tungsten has different phases. There's an alpha and a beta phase of the tungsten, and depending on how you produce your thin film, you can also tune this transition temperature. They have also this possibility of rejecting the surface, near surface events, because they have also this interleaved electrodes here. You see here also on the real detector, so they look even quite beautiful, and they achieve at such big detectors thresholds of 70 eV, also a bit lower some detectors, and yeah, they have also sensitivity in this standard scenario down to 1.5 GB using a different analysis I summarized here. Here just again to show you this with the particle surface rejection. So depending on where you have your interaction, you then have the holes and electrons drifting to one side or the other, and so to the same side or to the one side and the other side, and like this you can reject such events, which is good, because imagine you have, for example, that the burst is this led to 10, so you have an alpha decay, and imagine like the alpha decayer sits on the copper holder, and then you get the nuclear recoil. So it's alpha decay is a back-to-back process, so you get your nuclear recoil in the direction of the detector, which could mimic a dark matter signal. It's a nuclear recoil. And the alpha escapes to the other side, so to the copper bulk, and you miss it. In this way, you have a signal which you cannot discriminate from a possible dark matter signal. However, if you, of course, can reject the surface, this is a really good thing, and suppresses the spectrum. Okay, so Super CDMS, they run in Sudan lab, but then now they are building in Snow Lab, which is also a big lab in Canada. It's part of a nickel mine, I think. And this is still working. So it's not like in Australia where the mine is not working anymore, but it's like really a mine which is in operation, and they dedicate some area in this lab in this mine for physics. And if you are a physicist and doing work there, you typically you arrive there, then you dress as a miner, and then you walk first, then there's some lift, and you go down 20 minutes with the lift in the shaft with the miners, and then it's very hot because you go down, right? And then once you're there, you have to walk quite a bit until you arrive at this experimental area, where then there is some gate where you take off your miner clothes, and then you go in and you have a shower and you get a clean room clothes, because this whole area is a clean room. So you have to completely wash yourself and dress up again as a clean room coat and then you work. And then you can only go out when the shift of the miners start and stop, because this lift is not going for everyone, but just at this shift changes. So it's quite it's quite different to working in other labs like this Modern lab or Canfranc or LNGS, where there's some shuttle services bringing you in and out, and they are not clean rooms. Okay, just as a side note, so Super CDMS is moving there, and they're building a big setup there for the next phase of Super CDMS. They have also 2 test facilities, which they call Qt. This is also at Snow Lab, just the neighbor of the big Snowbox. And then there's Nexus, which is TriStat at the Fermilab. So therefore, at the moment with these big detectors, they are not taking any data because they're moving and setting up a new setup, but they also started to go to this lower mass detector. So there's a lot of R&D ongoing at the moment. And here you see just an example of a 10-gram detector, which they optimized actually for light detection and now used for some light dark matter detection. So they operated this above ground, and you see, they could draw a limit. So they arrive at a threshold of 20 eV, and they can draw a limit which is world leading below the one of Crest in this parameter space there. So you see there's quite a lot of not explored parameter space, and even with just one detector, so it's just a small thing, a prototype, you can make a new physics result. Okay, so this so far now for the cryogenic experiment. So there was I told you now about Crest, Edelweiss, and CDMS, and now I will just add on one slide a short, brief summary on just an ionization detector, which is called CDEX. So this is a detector consisting out of an germanium diode. So here's just a picture of it. So it's a simple pin contact germanium diode, There's 10 of them, each is, I think, 1 kilogram. And yeah, they are located in this Jingping lab in China, which is now the world deepest lab. And yeah, what is nice about this technology is, of course, that you can scale it up. Background is quite low because this material you can get very clean. The only disadvantage is, of course, that you have a single channel detector again, where you cannot discriminate between nuclear recoils and electron scatterings. Here you see a sketch of their setup. This was CDEX 1, so I didn't find anything on CDEX 10. I presume it's the same, just they put not only 1 crystal, but 10 of those. And yeah, they arrive at very good energy thresholds now. And yeah, they're working now on also the upgrade in increasing in mass to CDEX 100 and then 1 ton. Yeah, just again, this plot. And yeah, now you maybe know a bit better what all these lines is about, because I told you what this experiments is about. And yeah, you see, I mean, they're all, so the screen lines, they're all in this low mass to middle dark matter mass region. Yeah, I should mention that with this Migdal effect, of course, also this liquid noble gas detectors they are achieving sensitivity in this low mass region, which is of course also very interesting and very important and nice. Nonetheless, of course, there's a lot to be done. I mean, if you compare here to there, you see there's quite some room for improvements and for some future detectors. So a lot of people can put their hands on still until we can check this area out there. And yeah, so what's next for this low mass searches? Yeah, just put together one slide what came to my mind, from all the discussions and workshops I was also participating to in the last month. So yeah, lower background, of course, is always good. So you try to improve your facilities and upgrade them. Also the detector purity, of course. Then, yeah, you want to lower the threshold because you want to go to, less than this 150 MeV, which is now achieved. In this case, you have to optimize your detector technology. And in this, there's, as I have shown you, I guess you get already the right impression. I mean, there's a lot of different small experiments doing a lot of different detectors. So there's not this standard detector and you say you scale it up and you do it 1,000 times and then we do a measurement. But people are trying out to optimize their detectors, trying different designs, techniques, and yeah, there's a lot going on at the moment. Of course, it's not enough to go lower in threshold, but at some point you have to also go lower in sensitivity. And in this case, it's a pain because you have to increase the number of readout channels. And this means for such cryogenic detectors, for example, I mean, it's not so straightforward. You have to make a bigger cryogenic facility. I mean, we have seen with Corve, you can, of course, do this up to 1,000 channels, no problem. But yes, one has to do it, and it's quite challenging as this cryogenic, also dilution refrigerators. They are now commercial machines, but still you have to do a lot of design and thinking in order to make it and work with your experiments. Then an important point I want to mention is that all this cryogenic detectors, they see this excess when you go below 200 eV or so, which has an origin we don't know. So there's a lot of investigation also going on at the moment. There was just 2 weeks ago, there was a workshop, which was called the Excess Workshop, run by Hefi in Austria. And there was, it was really impressive. There was like 140 or so participants to this workshop from all these experiments, because obviously all of them have the problem and don't understand it, and all would like to learn about the origin. And there's also what is very nice. So the experiments, they are open to share the data and discuss openly, which I found very refreshing, because this in the past was completely not like that. So this is, I think, a very positive improvement and change. Yeah, what I want to say here, which is also a bit, also my opinion, I think what the excess could be about is some thermal relaxation. All the solid materials, of course, when you grow the crystals, they are single crystals, they are perfect, but not perfect. So one can imagine maybe when you cool them down, the crystal feels some stress, and the stress with time can release. So you would get events when maybe crystal bounds break because there's really tiny cracks or so, or some also relaxation processes happening at some atomic bound level. Because in the end, we don't see this at the keV scale, but we see this at below the 200 eV scale. So yeah, this of course can be come from such origin. And yeah, we started now to study solid state physics a lot in this direction, and there's also a lot to be learned, which yeah, is just new also for this low temperature community. Okay, so I guess this was all I had on now this low mass dark matter and on dark matter in general. And yeah, the next part of the lecture would be on experiment solution for this neutrino-less double beta decay. I don't know if you have still questions, comments on what I just said for this low mass detectors.
Please raise your hand if you have any comments or questions. Walter?
Is it possible that these low energy excesses, at least some of them, could be interpreted as new physics?
Yeah, yeah. This of course was also. I mean, maybe I have to say more than just a couple of words. I mean, here with CREST, for example, you see from different detectors. So this is 4 different detectors, and you see the energy spectrum and this rise, which starts more or less, below 100, 200 or so. And I mean, if you have different shapes, it's difficult that you say they see the same physics origin, because it should be quite comparable, right? So we have, but also the suspicion that maybe it's not only one effect. I mean, maybe there's no physics, but plus there is also, this cracks, for example, which produce some kind of, background, which also points, so this time dependence we see. So we see that this, on the basis of 200 days or so, this events decay, a part of it decay, so you can fit, but this is not true for all detectors. So, I mean, maybe this goes a bit in this direction that there could be some issue with this kind of relaxations. This also may be true for the germanium experiments, but there can maybe also be other effects. Yes, also new physics, other backgrounds we so far do not consider. I mean, there's a lot of question marks, and I guess these question marks appear more or less to all the people in the community. Therefore, there was this workshop and this huge interest. I mean, there was not a conclusion. There was not this, okay, it's that. I mean, it's just the start of saying, okay, we all more or less see that. We have to study it in more detail. And it's not so trivial to study it, because you have to run for a long time. I mean, it's also, for example, for CREST now, if you want to see this time dependence, and you know this has some 200 days or so, you have to run for a couple of years. But this is, of course, I mean, it's a lot of time, right? You run and then you do your next test, because it's not that in between you can do other tests then. So it's quite a challenge, I would say, and it's quite a mystery to solve. Yeah.
Okay, thank you.
Other comments or questions? Okay, I'm sure that at the end of the talk we can have some discussion. Please go ahead with this chapter.
Okay. Okay, so yeah, now completely different topic, also different energy scales. So now we go from EV to MeV. We look for the neutrino-less double beta decay. As I already told you, so this has a characteristic line at the energy of the 2 emitted betas here. So this is this peak. Then you would look for as a monochromatic line at the Q value of the very isotope. Just also to mention again, you have of course always this 2 neutrino double beta decay, which you cannot avoid because this comes with the isotope. And your detector, in order that you can see then this small peak here, because it's there's quite many orders of magnitude in between the rate of both. You have to have a good energy resolution. Otherwise, this will be somehow overlapping or washed out. There is different kind of isotopes that could undergo such neutrino dust beta decay, and among them, for the solid detectors now, there is germanium 76 with a Q value at 2 MeV around. There is the molybdenum 100 around 3 MeV, and the tellurium 130 at 2.5. I write here higher Q value, less background. We can show you this also in a minute. And then of course the other important factors that you have to offer isotope also then in your detector to look for this decay. So the more the better. So enrichment is something which is of course wanted. Enrichment, however, is expensive, especially if you cannot, for example, make a gas and use this centrifugal technique. Therefore, it's also good to look for elements which have maybe already a high natural abundance, like the tellurium. So this is used in the Quora experiment, and also, I guess, for this reason. Then there's molybdenum and germanium. They are more or less in the same region. Then there's very interesting isotopes like the calcium, which has a very high Q value. So you would have an experiment which, you would expect a really low background at that energies. However, the abundance is very low, and the enrichment is not possible via gas. So in the end, this is a very difficult material you wouldn't use. So it's a bit of, you cannot always have everything, but you have to make some compromise, of course, at some point, and in the end, it should be also payable. Oops, does it work? Okay. So what is then what you look for with the experiment? So this measurable quantity is the half-life. And this depends then on this effective Majorana mass of this, the neutrino exchange between these two electrons then. And the other factors here is nuclear matrix elements. This is something which comes also with some uncertainties. Then there's the phase space integral. This axial vector coupling constant, the GA. And as I said, here's this effective Majorana mass. And so this is a bit, that what we can do here. You see some calculations of this nuclear matrix elements with different methods and their agreement. So this is some uncertainty which comes in here. And as I said before, the lower the Q value, the more background you have, or let's say higher Q value is better to have lower background. And this is shown here. So this is a germanium spectrum measured in an underground lab. And you see until 2.6, 2615, this is the 208 thallium line. This comes from natural decay change. There you have, so this is the highest energetic one. You see from there on, then the background is quite almost an order of magnitude lower than on the other side. This is, of course, important. The sensitivity formula is given here. So you see that the main driving factor is the mass you have, the measuring time, the background, and the resolution. Of course, measuring time, you don't want to measure 100 years, because then you cannot see anymore the result. So in the end, this is also somehow a trade-off. But of course, the best is if you have an experiment which is background free, because then your sensitivity scales with the exposure. Right? So this is I guess also a take-home message for that. The strategy, maybe I already said, so you have to have low background. So of course you go underground again, you purify, you take care about the body purity of the crystal. If you can, you choose a high Q value. And then there's somehow this trade-off of, xenon is easy, but it's liquid, has less good energy resolution. Calcium could be a crystal, but it's difficult to enrich. So it's a bit like you cannot have everything again. And tellurium has a high abundance and is also used effectively. And excellent energy resolution is of course also good to separate then the two neutrino from the neutrino-less in the spectrum. Some history now to the Quora experiment, which is the first experiment I would like to tell you a bit about. So this started all with very small, couple of gram detectors in the 90s. So this was, when you remember what I said in the first lecture, and that's the time in 1987 where people thought of using such cryogenic detectors for isoparticle physics. There was then also this first LTD conference, so this was more or less all there, and there the first detectors were operated. So this was very exciting times. So then there was, this was going up a lot. And then there was the first bigger array was this Mi Beta, then Coricino, Cuore Zero, and now Cuore, which is this huge array operated at Gran Sasso. And yeah, about this I will tell you now more. Okay, so yeah, they have tellurium dioxide crystals. Each of them is 5 by 5 by 5 centimeters. Then they are mounted in this kind of frame here. So 4 of them. Everyone has a mass of around 750 grams. And yeah, then you have per tower, you have 13 of this 4-pack crystals here. This is then 1 tower. And in total, you have 19 of such towers. And this makes then this 988 kilometers that you have. The tellurium, I should say, is here natural. It's not enriched. It's just as you have the isotope from nature. Then this is a cryogenic experiment, so it's operated at around 11 millikelvin. And yeah, the goal is to look for the neutrino stable beta decay of tellurium 130. Then the mass that you have effectively of this isotope is around, from this 742 kilogram is the active isotope mass is 206 kilogram. And yeah, just again to remind you, the Q value is on the bad side of the thallium line, so it's below the thallium line at 2.5 MeV around. The energy resolution that Cuore aim for and also almost all achieved is 5 kV with half maximum at this Q value. And a background in the region of 10 to minus 2 kV kilogram in year. And yeah, this is the goal for the sensitivity. So it's 9 times 10 to the 5 to 25 years. Then just a closer look to how this looks like, the crystal. So here you see this milky tellurium dioxide crystal, and then here you see this nice NTD sensor on. So there's 2 gold lines for the biasing, and yeah, they are glued on the crystals by some epoxy. And together with the NTD comes then also on the other side here a heater, which is just a heater for fixing the energy scale. So you send pulses there and you see if the detectors run stable in time. With such NTD of Cuore, you can measure temperature increase is around 100 microkelvin per MeV of energy deposition in such a crystal. Okay, a couple of pictures, because I always found it so impressive that you can do such a big experiment. So you see here then when they started to mount the towers to this plate, which then was mounted to the mixing chamber. Here you see them during mounting of the towers, and there's 5 towers, 9 towers, and then there's all the 19 towers mounted. And you see in comparison also to the people that this is really huge. Carlo yesterday already, I think, told you a lot about cryostats and the pain, and also maybe the reason why there is a cry in cryostat, because there's a lot of problems you can have with this ladies. But in the end, they are also fantastic machines, because they can provide such low temperatures, even cooler than the known universe. And so just maybe a few details. So you see here this detector array, and the lowest or the coldest part of the solution unit is the mixing chamber, which is having a cooling power of this 5 microwatt. This seems to be very little, but this is actually really a lot. And yeah, apart from that, that the detector already weighs has a mass of about 1 ton that you cool to this millikelvin temperature. They have also here lead shield to shield radioactivity, which comes from the cryostat itself. So this is very important because Cuore, they measure only the heat signal, so they cannot, for example, discriminate, as we have seen with CREST, between alphas, nuclear recoils, and gamma betas, but they have also just an energy spectrum. And for them, of course, looking for this the neutron-dust double beta decay, and like degraded alphas are a dangerous background. So you have to really care about the background budget you have. So therefore, they have here this Roman lead inside and also here around. But this here is really at a millikelvin temperature, or let's say that this decouples at some point, but it's in the code. Genau. Here also some pictures of this, how this looks. So this is this outer lead, and this is the lead sandwich they hang on inside of the cryostat here. And yeah, I guess Carlo already told you that this cryostat is sold as the coldest cubic meter in the known universe. So this I find also very nice because it's a big achievement. And yeah, it's nice. To the shielding already said, I guess, enough. So what about their result? So here you see energy spectrum, and you see here a peak. This comes from cobalt-60, which is a contamination they have. And then here you see the region where you would expect the peak if there would be the decay. And yeah, you see, there's no evidence with the best fit, and the sensitivity they arrive is 3.2 times 10 to the 25 years. And this corresponds to an effective Majorana mass of 75 to 350 millielectron volts. This they published last year already, and this is from an exposure of about 400 kilogram years. So then, of course, they continued running, and I know that since a couple of weeks, I think they arrived at 1 ton year. So, and soon there will be also a new release of data. Maybe also what I should say is about the background budget, because this we can also compare them to the other experiments I will tell you about. So this is in the region of 10 to the minus 2 counts per kilogram and year. And yeah, here's the energy resolution they achieved. So they were aiming for 5 and arrived at 7. The main reason for that is that the technique or the cryostat used is a dry dilution refrigerator and not a wet dilution refrigerator. And they come with this so-called pulse tube coolers, which provide the 4 Kelvin. And in this wet coolers, you have the helium bath for doing that, and then the bouquet pot. And yeah, this pulse tube coolers, they have what is called a rotary valve, and this is a source of quite some vibrations, which can, of course, then also affect the detector performance. The next experiment I want to talk about is Gerda. So this is just the neighbor of Cuore in the LNGS underground lab. So there's hall A, where there is Cuore, then comes CREST, and on the other side of the road there is then Gerda, and behind there is ABOD, which is, however, in the decommissioning phase now. And yeah, so what is Gerda? So Gerda uses germanium detectors, so looking for the double beta decay of germanium-76, and they use this diodes, as I told you in the last lecture. So they have this BG, but also the coaxial detectors. And yeah, here I would like to show you how clever their detector principle is. So if you would have this double beta decay in a detector, okay, you deposit the energy and you measure it fine. Now, if you have, for example, some muon passing, it would produce light here in this liquid scintillator, argon veto. And yeah, you can reject it because you see then also the light in the the water, but also in the argon. So this is something you can recheck, because here in this argon, they have also this optical fibers which guide the light, and then they have the photosensors to measure it. So this is an active veto which is just around the detector. So the germanium is really immersed in this liquid argon. So there's nothing around, it's just really inside this liquid argon. Then, this liquid argon veto also is helpful for gammas, because you can, if you would have this, the light from the argon, of course, can always discriminate it. Then, if you have a gamma which makes an interaction in one crystal and then goes further to the next one, you get what is a multi-side event. And you can use this anti-coincidence cut to remove such kind of background. And then, you can even do what is called pie shape discrimination. So if you have because the crystals are quite massive, so if you have a gamma interacting more than once in your detector, you also see this by doing this pie shape analysis. And also this is true for example, surface events, so alphas making interactions on this close to the surface, or betas, I mean, they don't reach so far. I mean, they reach a millimeter. So this is fine and can be also discriminated. And so this is in the end really a concept which allows to have an experiment which is background free. Which is background free in this region of interest, which is really amazing. And they have also a good understanding of what they measure. So here in gray you see just the spectrum or the data just is taken, and then you start to apply cuts from this liquid argon veto and also pie shape analysis. And what you end up in the end is like in the lower energy region, you have mainly this 2 neutrino double beta decay. And then, there comes a bit from the potassium, you see here, potassium 1442. And a bit here further up, there's then the bismuth and also the gamma line from the thorium. And but in the end, all alphas here at a higher energy region, even they can be suppressed. So this is really powerful. And here it's indicated the region of interest. So this is the Q value plus minus 25 keV. And they don't have events there. And if you then do a fit to that to understand your sensitivity, so they arrive at 1.8 times 10 to 26 years. So this is an order of magnitude more. And it's just amazing how low is their background level, because this is, so here in green it's indicated. So this is in the 10 to minus 4 per kilogram KV and year, in comparison to, for example, Core, which had 2 orders of magnitude more. So this is really nice. And there is a pendant to this GERDA experiment, which is called the Majorana demonstrator, which is an US experiment. And they simply do more or less the same thing. Also cryogenic detector, not immersed in liquid argon, but in a cryostat. They have excellent energy resolution. I should mention here it's 2.5 kV at full width half maximum at the Q value. So this is really amazing. And here you see their results. So they have not such a low background as GERDA has, because they don't have this intelligent technique in vetoing everything which comes from outside. But nonetheless, they arrive at also good sensitivity in this 2.7 times 10 to minus 5 per year. So this is both experiments. As I said, they work with the same target material, with the same detection technique. And they have now certain results. And if you want to now get better, you have to increase in target mass, because they were running only a couple of 10 kilogram. But if you want to get better, you have to increase to a couple of 100 and then a ton. And so this brings me also to what is next with this searches. So yeah, the goal is, okay, so the best limits so far, they come for germanium, they come from Gerda, and for xenon, they come from Kamland, so a liquid experiment, and yeah, for tellurium, they come from Cuore. So this is a bit the status of today. And if you look in this, in this plot here, where you have the effective Mariana mass plotted versus the lightest neutrino mass, you see that in this gray shaded region, this is where now the experiments sensitivity are. And the goal is now to cover this inverted region and also go further. And to do that, you have to have more target mass, you have to have less background. And yeah, this is very challenging. I mean, these experiments are really very, very difficult. And yeah, to do that, there is here a summary on the experiments on the market, let's say. So there's the bolometers with Cuore qubit. Then there is this big scintillation detectors, also the semiconductors with Gerda, Mariana, and Future Legend, and also TPCs. So there's quite a bunch of experiments, but of course not all can go now on in increasing target mass and doing bigger detectors. So there has to be some kind of down selection, because especially this enrichment comes with huge costs. And yeah, for the solid detectors now, which we should talk here about in this lecture, I guess it's Majorana and Gerda, they can do quite good, because they are both doing quite good, and they put this together. And yeah, in the end, as I said, so Majorana has good detectors with the best energy resolution, and Gerda has this zero background approach. And yeah, in order to now move on, I mean, they agreed to go together, and they call this new project Legend. And yeah, what they want to do is in a two-phase approach, now do Legend 200, with increasing from this 100 kilogram, they have together to 200 kilogram of germanium, and then to 1 ton. The first phase, so this Legend 200, will be done at Cansasso at the moment in the commissioning phase. They would like to arrive at half-life of 10 to 27 years now in this next stage, and then larger than 28 for then the stage afterwards. It's not clear where Legend 1 ton would go, if this would really also go to Cansasso, or if this would go to Snow Lab. This depends a bit on, I would say all the collaboration and also the funding. But yeah, the first step is now this 200 kilogram at Cansasso, which should still start data taking in this year. So this is very exciting. Then for Cuore, the follow-up is called qubit. This will point on molybdenum 100. And the main reason is that, as I said before, the tellurium dioxide is not a scintillator. So you can just do a single channel readout, and then you have always the problems with the degraded alphas, which make your big background in the ROI, which is a 2 orders of magnitude together, for example. So there the logic move was on going to a crystal which produces also light, such that you can have beta gamma events discriminated from alphas and also degraded alphas, which would just make a band here. And yeah, in such an experiment, you can then just discriminate them, and this will allow you to go to also very much lower backgrounds. And yeah, so also there, so the aim for discovery sensitivity is in 10 years, 10 to 27. So there's a 1 order of magnitude together. But yeah, I guess it's important to say also that it's, I mean, you cannot throw all the money and the manpower on one experiment, because if you then would make a discovery, unless you don't find someone who confirms you, it will not count. And as such experiments have really a long preparation time, and I mean, only the procurement of the isotope, I think here on the, was it on the Legend slide. I've seen it. I mean, this takes a couple of years. I mean, it's just not something you can just decide for starting. I mean, you cannot say now we wait 15 years until Legend made its job, and in case they would see something, we start then to plan another experiment which could confirm in case or give more information. So this doesn't work. So one has to, I guess, do some kind of parallel strategy in having experiments which have different detector technologies in case to offer discovery, to have also the chance to cross-check each other. So I guess this brings me almost to my end. So I have one more thing, which I promised is this, the CCDs. So they the silicon ionization detectors, which are sensitive in particular to electron scattering, which allow you to do this really low mass dark matter detection. So this, so how they work is in the end, you have a CCD, this you maybe know from your camera. So it's a pixel. If you have an ionization, this drifts and then towards the gates, and then you can read it out. And as you have not only one, but you can have an array. In the end, it's like taking pictures, right? You can construct such decays then. So you have the non-alpha, the muon, the electron, they have all characteristic paths, and this is nice because it allows you for particle discrimination. And there's an experiment which is called DAMIC. This is at SoUP, and they were running a couple of years ago, I think 7 of these CCDs, and they achieved very also low and promising threshold of 50 V. And they were looking mainly for electron scatters and also other dark matter candidates. And they have also new results for now nucleon scattering. And as the other cryogenic detectors, as I learned also in this workshop, they see also some excess which they don't understand in this region below 100 eV. There's now also an upgrade of this DAMIC to DAMIC-M. This will be done in France, where they would scale up to from 7 to 50 CCDs. And this is something which is in preparation at the moment and will go online in 2 years from now. Very similar to DAMIC is Sensei. This is operated not underground, but the Fermilab. And it's in principle the same as DAMIC. And they also run such CCDs and achieved quite also some good sensitivity for this electron scattering. And also they put in a proposal for now scaling up and doing a bigger array of the CCDs in order to study with higher sensitivity such possible dark matter candidates and interactions. This now really brings me to my end, and I think if you have questions or so, please ask me or write me or as you wish.
Thanks a lot for this very nice and extensive overview about solid state detectors, Carolina. So let's see if there are questions. Please raise your hand. Maybe Walter, I don't know if you have your hand was already raised and you forgot to.
Yeah, it was already raised, sorry.
Okay, so there is a question by Vincent.
Yes, hello. My question is about the neutrinoless double beta decay detector. And do they have a track recognition dispositif to be sure that the track comes from the same place and is a double beta decay?
Mm-hmm. Yeah, so this experiments I was telling you about, so Cuore and Gerda, they don't have this. But there is experiments which have trackers, which I think is called SoUP2021, which is also in France. And they have thin tracking detectors. So there they can look for the topology of the event. So this is a feature which these other experiments I have shown you today cannot do. The problem of, I think, this kind of tracking detectors is also the increase in mass in the background. Therefore, they are not, they're not among these now detectors which are discussed for scaling up. But yes, so there exist detectors which can do that event topology reconstruction.
Okay, thank you.
Other questions? Okay,
so it seems not.
Yeah, please, Marco.
No, go ahead, David.
No, I was just saying that if not other questions, we can close the session here.
Indeed. So we thank again Caroline for the nice presentation. We remind her if she can either upload the slides of the second part or let us have them and we will manage.
Sure.
And we will reconvene at 2:30 in the afternoon. Gabriella Sartorelli will chair the afternoon session. And so you can, now we have the lunch break. In the second half of the afternoon, we will have the hands-on session on the statistical tool. If you have any